Okay, thank you very much for the kind introduction, and I guess I'll add a little bit. You mentioned about my work with NSERC, and so Russ O'Hara, Daron, Mark Yungat, Waxanagede, Waganyatan, Green de Waxanazare. So obviously just that my Mohawk name is Russ O'Hara. It does mean he builds a bridge because I got my name recently in the line, but anyway, so it has to do with this work. So I would like to acknowledge my co-authors, Hamza Hajalu, who I think is going off to chair a session on rational design with fire from Carleton University, and also Bronwyn Charlton, who is working with me now in a postdoctoral role at Queen's. And so this is coming out of work that we've done over the past few years, as mentioned, and really just trying to give an overview what we had been making for recommendations that's in the commentary for the 440 code and what we're talking about in this paper. So basically I'm going to talk a little bit about the background research steps done to come to this. What are some of the issues with particularly glass fiber reinforced polymer materials at high temperature and for reinforcing concrete? And then what are some of the design approaches, and specifically for the ACI? Also mention a bit about some of the Canadian standards. We're all here because we know about the wonderful properties of FRP, the high strength, resistance to corrosion. One of the challenges when you're with elevated temperatures or fire concerns, that there is reduction in capacity of the GFRP materials, and so we really have to take that into consideration with our designs. There has been quite a bit of work that's been done on the GFRP reinforced concrete. What I'm going to present here is mainly the work that we have done, but there are lots of others who have done work elsewhere in Europe, etc. So there is a good body of evidence substantiating beyond even just the tests and the work that we have done. As a result of that, we do have some updated recommendations for the code. So some of the key challenges, though, relate to how we try to evaluate whether or not structures are safe in fire. And well, my colleague Luke Bisbee could talk a lot about how inappropriate these types of testing is for structures and how they don't actually represent what actually happens in a fire. But I won't go into great depth as he would. But one of the challenges, particularly for FRP, is the difference in the way that we use the FRP as reinforcement for concrete. And when you design a structure for steel reinforced concrete or many other structures, the design is largely guided by strength. That's your governing parameter. And so for the tests, they're all geared to finding out, well, how strong is the member, and then we will figure out what load to apply to that member. But we don't, well, you can't do that with GFRP, because if you design it for strength, you'd have, I mean, nobody would walk on it because the deflections would be massive. You would have really wide cracks. Everybody would say this thing's going to be falling down. So of course, we design for serviceability, and we also have restrictions in the strength. We've actually just increased it to 30% from 25%. So that for the long-term stresses in the bars, we never expect there to be more than about 25 or 30% of its actual tensile strength in normal circumstances, which is very different than what we have or allow for steel. We don't have those types of restrictions on steel. You might easily have 60% of the strength or more in a structure under its regular loads. So this is a challenge with sort of the fire testing community, is that it's all based on those assumptions for steel which don't apply for GFRP reinforcement in concrete because of the different behavior of the materials. We have in Canada in the CSA S806, which is for building structures with fiber reinforced polymers. There is a semi-empirical approach for the fire resistance. It is based upon the minimum concrete cover, but unfortunately it's still using this idea of the strength of the FRP as being the approach. And really this was put in because this is what's done for steel reinforced concrete, is that when steel reaches, it's about 600 degrees Celsius, 1100 degrees Fahrenheit, then steel loses about half of its strength. So what we have done in the Canadian standard is say, well, we'll just say, well, when does the FRP bar reach half of its strength at what temperature? And it recommends about 250 degrees Celsius, that's almost 500 degrees Fahrenheit, 325 for GFRP bars, and just over 600 degrees Fahrenheit. That's once again half of the strength is around when you get that. And some of our work, maybe these values are a little bit higher, which we'll show later. But these are some of the curves that are used for guidance for doing slabs. And so this is quite a thin slab, a 5-inch slab, basically 120 millimeters. And so you can see that depending on the cover that you have, if you have here, if 40 millimeters, that's about 1.5 inches. Then for 325, then you would come down here, and then that would be good for a 1-hour rating for this thin slab. So that's the way how you could use this curve. If you wanted to get a 2-hour rating, say up here, you'd have to use quite a bit more like 60 millimeters of cover to achieve that. So, and this work, as you can see, 1998. So this was what Luc Bisbee did in his spare time when he was doing his PhD. I think it is a chapter in his PhD as well. So anyway, but generally in sort of looking at GFRP and fire, we've done a lot of work, much more, and certainly on the material testing, and that was sort of the big, when we were doing this work 25 years ago, it was certainly something that bothered Luc considerably, as about, like, we really didn't know anything about the material properties and how stuff really worked. So we did full-scale testing, however, and then we've also done a lot of modeling. I'm not going to talk about the modeling today, so I'll save you from that. So here's the information about the tensile strength at high temperatures, and this is more recent work, and we've done, in the last 10 years, with 3 different types of bars that are fairly common. And now we're just looking here at the tensile strength with temperature. And so you can see here we've taken as about half of the ultimate strength, showing a curve here. And you're seeing we're getting things that are sort of in this range of something like 300 to 400 degrees, depending upon the type of bar for that. So we're sort of doing this work to sort of see, well, how does that compare against what we have in the S806 document? But then you look at, but we're limiting that you can't have a sustained stress on the bars to 25%. None of these bars at any of these temperatures comes down to that level. And you have to remember what we did. In a fire, it's this idea about combinations of events. So we design for extreme event when you might have a really extreme load on a structure, and so maybe you will need most of its, the strength of the reinforcement, et cetera, in that case. However, in a fire, you don't expect that in the fire you will also have the largest load. Well, generally you won't, because, well, if it's people, they're going to be leaving. Let's hope. So that, but to say that all sincerely, hopefully all the people can be evacuated before we have to worry anything about structural integrity. So, so that you realize that, you know, in a fire, the stresses, they're going to be in this level of what we restrict in the design code to be no more sustained stress than about 20 to 25. So why do we have to have half the strength if we're never going to have that stress present in a fire? So there's one thing. And you can see these are actually the tests that we did. Some of the temperatures that we have, and these are the temperatures in the center of the slab with time, and you can see here we're getting up when you have 20 millimeters, that's about 3/4 of an inch of cover, that you're getting temperatures up to 600 degrees, that's close to 1100 degrees Fahrenheit. And in these cases where we had 40 inches of, or 40 millimeters, 40 inches, yeah, massive cover. 40 millimeters of cover here, which is about 1.5 inches. So you can see you're easily getting up to 400 or 500 degrees Celsius and over that. So we're well into this region in the bars, but we're still carrying all the load that we have applied in this test. So even though we've well exceeded and we're out in this region in these tests, these slabs weren't failing. And so this is where anchorage and the bond of the reinforcement becomes much more of an issue. So also we've done, so we have done the full-scale test, but we've also done pull-out tests to try to evaluate the bond of the reinforcement. And this shows, unfortunately, where we really are affected by the high temperature is the bond of the FRP to the concrete. So it's not so much about how strong the bar is at high temperature, it's how well it's anchored. So unfortunately what happens here that you get a severe drop in the strength at a little over 100 degrees Celsius, that's like 250 degrees Fahrenheit. And this is largely around what is people commonly talk about as the glass transition temperature. And that's mainly because the bond is governed by the polymer. And so when, you know, basically it's holding the fibers together and it's also bonding to, you know, that's where all your chemical bonding to the concrete is occurring. So when that degrades, then you're losing most of that. And so you lose most of it. The interesting thing is, even at these much higher temperatures, you are still retaining some bond. So there is bond that's having all, like the polymer is really destroyed, but you still have fibers, you have friction, you have some other things that are giving you some sort of bond as well. So you don't lose it completely, although you're down to something like 10% of what the original bond was. And you can see the most recent tests, these are the ones in the start, and they're sort of showing comparable performance to the other bars that we've tested previously. And so I've already talked a bit about this, that we're getting 170 degrees centigrade, 340, 350 Fahrenheit, we're losing about 80% of the bond. And you can see that you're losing that very early in the test at the bars. So these are the red curves here. That's the bars that were actually the cover that we had embedded. So they're experiencing much higher temperatures in the center of the slab, but we're not having failure. So we lost the bond in the middle, but at the ends, we're still retaining. So in these tests, what we had was end anchorages at each end of about 8 inches, 200 millimeters, that were protected from the fire. And we tried to reduce that as much as possible, but this is basically as short as we could get them in the test, because we knew we wanted to focus and see what happened more on the bond performance. And so you can see in this end zone here, where you're going, the temperatures in these bars are much, much lower. So that at 3 inches from the end, it's only 100 degrees centigrade, so a little over 200. So you're only just affecting the polymer at that stage. And you can see here that visually most of the coating is intact. It's starting to peel and things like that. But this, of course, is where it's all burned away in that higher temperature zone. But it just shows that we're getting quite a bit of strength developed even with these very, very short embedment lengths in the relatively cool zones. So that's where we sort of look to say, okay, well, how can we implement this into the codes? And so we said, well, let's say that we should have embedment into the support of basically a development length. And that's basically what we have here for the bars, is to say, well, the best thing to do would be not to splice bars where they might be exposed to fire and then embed into the support by 12 inches or 20 bar diameters is basically what we're suggesting. And with that, it's suggesting with 1.5 inch cover that you would get a 1 hour fire resistance. Now, in those tests, the actual tests that we did, they survived for 3 hours, and they actually only failed because when we increased the load. And to start with, should mention, because I talked about the load, that the load that we applied was about double what we would ever have expected in service conditions based on service levels. Do you remember the exact percentage of the ultimate it was, Hamzy? 45%. It was 45% of the ultimate. So typically you might get, in a steel reinforced one, you might get closer to 60% of the ultimate. So we were lower than that, but still, I mean, you would never want to have a slab design that had those loads applied on it, because the deflections were very, very large for the span under that, and certainly a lot of cracking. But it certainly shows that doing this is, going to be very conservative, because, we only had 8 inches, and we're suggesting at least 12 inches, and into these cool zones. However, we've also said that, well, if you can't get that far into the slab, then maybe you can do some other things, thicken in these areas, or provide some external insulation, et cetera, to do that, if you can't quite get that. Now, we know practically trying to do this might be problematic. I do think that in many configurations of slabs, particularly, as long as if you have edge beams or anything like that, or columns you can anchor into, I think you can largely achieve this without doing anything else. Maybe look at how you're laying out your reinforcement, make certain you have lots of bars in your middle strips and things like that, and get them into the, and if you have drop panels, etc. But it's going to be hard if you don't have drop panels or you don't have other things like that. So you could, in those cases, perhaps look at some sort of protection from thickening the concrete, providing external insulation to do this. And so that's what sort of some of this next work, and I know Hamzy is really the one leading this part, but really looking at different types, using gypsum board for this insulation, or spray applied applications, and also looking at intumescent paints to sort of look at, well, how can we better protect in these end zones and come up with, and that was not meant to be a football reference. But anyway, eventually we come to trying to get some sort of tables like this that they have in the IBC, the International Building Code, where you can just do something fairly simple, looking up concrete cover or the thickness of material, and then just get your fire rating out of that. So we do want to try to come up with that. I mean, Luke would be crucifying me here for talking about these simple things, because it's all about, okay, we got to figure, everybody needs to understand. And certainly I agree, people should understand better what they're doing, but it's good to have some simple things that you know you're going to be safe with these things. So generally, I mean, this is my thought. I mean, you really need to understand what's going on, as I emphasize. So like about the, it's really about the bond, and in the fire you're probably going to be developing this where you're in performance in fire, you're going to have, basically going to be an unbonded tendon that's anchored at the ends. But, those are fine structural systems. And really all we need to do is to prevent the building from collapsing. Now maybe if you want to design so you can have it retrofitted, maybe you would do a different parameter, but most of our fire design codes are all about saving lives and make certain the buildings don't fall down. So, and really we can do this safely with GFRP, and so I want to thank all the collaborators from National Research Council and Brahim at Sherbrooke, who helped build some of the specimens we had, and funding from NSERC, MITEX, and Ministry of Transportation of Ontario, and of course from our industry sponsors. So, well, thank you very much, and I'd be happy to, if I didn't run out of time.
We definitely have room for questions, so, okay, all right.
Mark, it's a great presentation as usual. Thank you so much.
Well,
and we built many bridges with carbon fiber pre-stressing strands and up to 150 feet long.
Yeah.
And before we built the bridges, we were asked to conduct full-scale
You did
test.
it. Yeah.
And we did a lot of fire testing in our full-scale fire loading chambers. And we usually do carbon fiber pre-stressing strands and also steel strands. And we compare, actually we go further by stainless steel strands. Would you elaborate on the comparison between the two, carbon fiber or glass fiber with steel and the structure that you tested?
Well, in our, yes, and I can't remember that was great work that you did, and I can't remember all the details of your studies. So some of the differences that you would have that that you may have in the pre-stressing configuration is about the fact that you have much higher sustained stresses, and so that, which has problems also for steel. And once again, Luke Busy would be better able to talk about it, because he's ended up doing a lot more work. But I know that there is problems with steel with the pre-stressing in fire on its own, but also the carbon does well in fire, just like the glass fiber. But some of the restrictions on the strength at the high temperature, so you may start to get problems in pre-stressing because you have much higher stresses. So one of the things that happens in a fire is you can lose about half of the strength. That's why a lot of these bars, they reduce to the 50% much more quickly, 50% of strength. Because what happens is you're no longer testing, at the high temperature, the matrix is basically all gone, and you're no longer testing a bar, you're testing a bundle of strands. And so now it has to do with also the randomness of the strength of the strands. So there's like bundle theory that can help describe some of that. So you will have that effect that you won't necessarily have in the steel. But then you also have steel under very high stress as well. And I've not done the comparable test, but I think that's some of the background that you need to remind me about what all your results showed. But yeah.
Thank you, never mind. Thank you.
Thank you very much for the nice presentation. What bar diameter did you consider, and according to your opinion, does the diameter?
So these
of the
are
bar
number 5 bars which are 16 millimeter diameter. So, and I think we did those. That's what we had in all of the slabs, right? And we did most of those in the other testing. So I think this would be. These results would be reasonable, certainly up to like 20, 25 millimeter. You know, if you go beyond that, you might start to get large, you know, some effects for larger bar sizes. People have done quite a bit of work with smaller bar diameters, more like, so I think most of the work has been done with even smaller bar diameters than what we tested here. That was one of the things we tried to do, was to move up a little larger with the bar diameter. Yeah.
Yes, thank you very much for your very nice work. Based on all your experience, did you came to some specific recommendation for covering of GFRP bars, or the only solution is to get protection? I mean,
Well,
based on your...
yes, I mean, well, so I mean, in our Canadian scenario, so we require 60 millimeters clear cover for steel in places where, if you saw the presentation earlier on the bridge, you'll see the corrosion problems that we have. And so the elements where you might want to use GFRP are generally when you're having a very corrosive environment. So the comparison is often with steel, where we need 60 millimeters of clear cover there. So certainly that's, but I think we can easily reduce that to more like the 40 millimeters with the GFRP, because we don't have to worry about the protection from that, and then we can achieve the resistance. Now, I know in the States they use a lot less cover than we do in Canada, so, but I think you can still achieve with like an inch of cover or an inch and a half cover, you can do the thing safely with the end anchorage, because it really doesn't matter how, well, okay, you don't want to get too hot in the middle, like you don't want to go much, so I think you want at least an inch cover, but 25 millimeters. So, but I know their post-tensioning systems here in the U.S. only have 20 millimeter cover.
For fire issue, there is no minimal covering? Or
Well, in Canada, we require an inch, 25 millimeter, even for steel, but I don't think in the States it's as much covering.
So my questions are a little bit more practical, which is, how far away do you think we are from having the fire resistance tables for, like, that would go into IBC? That's the first one. Maybe that's the easier one. The second one is, what's it going to take to get them adopted into IBC? Do you have any thoughts on that?
Yeah, so the two things, well, so I think we still, so there are two things there. One is, okay, well, how, I mean, we have to get the funding and then figure out the personnel to be able to do the work. And I would think, you know, for probably, you know, a couple of years to get the stuff for the IBC tables, maybe, to do the work, if the funding's available, right? So we don't have to even necessarily have the funding to do all that work. So then the other aspect is, how are people going to be interpreting how you have to do the ASTM test in order to accept it with an IBC? And I've talked about all the problems with that, the inappropriateness of that, particularly for, but it's the standard. So despite it being problematic and not rational, you know, in this application, you know, we could be blocked by people just saying, well, no, you're not doing it the way we do it for steel. And so that can limit. Well, yeah, I mean, yeah. But anyway, yeah, the whole, I don't know. Do we have any more time? There was one at the back here.
I'm good.
Oh, did I answer both of them?
Sort of, yeah.
Sort of, yeah, best I
didn't think
could.
you'd be able to answer
Yeah.
the second one too well, but okay.
Yeah.
Dr. Mark, thank you very much. The industry
Yeah.
definitely appreciated of all your work. This is more like maybe a question, and as we all know, GFRP is known to not be good in shear, well, I mean, not as good as everybody believes. On these slabs that you have tested, it was a fully nicely distributed loading everywhere on these slabs. So how would the punching shear or the shear of the bars, which at that joint of the cooler area in the slab, which you have a pretty sustained load right on top of that area. So is it safe to say that in fire application, the glass fibers are good to take the punching shear as well? I mean, that's what it, you know.
Well, that is, I mean, that is quite a different scenario, and I think as long, yeah, I'd have to think a little bit more about that. I'm not going to answer that because I have to think a little more about the mechanics that you have. I think there might be ways of doing it.
But the testings kind of proved that it was working fine because you have a very well distributed load.
Well, but this is not punching shear, so I just,
And that's
Right.
true way, and we don't, the code does not currently allow reinforcement for
Doesn't
two-way
consider-
steps. We don't consider
reinforcement
for
for
two-way
punching.
steps, yeah. So
Yeah,
I
so I
think
did-
that becomes a non-issue.
so I think that it can be done, but I've not really investigated it too much. So I don't want to speculate too. I've already speculated a little to draw upon. At least I've drawn upon more other work that I have done in other systems.
All right.
Quick question now.
Quick question.
You said this is just a fire. What about a dual extreme event of an earthquake and bomb?
Yeah,
Injection? Research?
We don't do earthquakes.
well,
Because your recommendations are only for fire. I'm just saying that in the code, but then if it's a dual event like that, then, I mean, I don't know if Canada has earthquake.
yeah, oh yeah. We have 3 earthquake zones on all coasts.
Right.
Yeah.
Earthquakes, dual extreme event, because you got the fire even before or after. Would your recommendations then do something like that as well?
Yes, I'm just going to say there. Yeah, we probably need to follow it for this, maybe less so. But I have done stuff in that more with the strengthening and other considerations, and done work with Alvarilki and Turkey about some of that, and looking at some of those issues. So I think we can do it, but I've not thought about these systems because these are just slab systems. So.
Well, with this, let's thank our
Thanks.
speaker.